Hello guys, I will introduce you to my process of building the model. I will also introduce the objective function and constraint of this mixed integer linear programming model. Our work is to assign a specific fleet type to each flight in a network. I use the word network because our work focuses on multiple flights on the same time, not just one. Or you can say that our work is to assign specific fleet type to a flight in a daily schedule. First, our objective function is to minimize the total cost, which includes both build cost and operation cost. For example, if you have two flights as shown in this table and three different fleet types, each fleet type will have a different cost for each flight. So if you need to choose one airplane for one flight, you can simply select the cheapest combination, for example, 100 and 110. Our decision variable here is XLT, where each small subscript represents the flight and the fleet type. The variable equal 1 if aircraft type 3 operates flight L and 0 otherwise. So this is our objective function, or you can write it like this. Our goal is to minimize this value, which is the green cell in the table. This green cell is some product of cost and decision variable, and it represents the total cost with h as same as the formula shown. However, this formula alone not guarantee that each flight had exactly one aircraft assigned. So we add the flight coverage constraint, which ensure that every flight is covered by one and only one fleet. As you can see, the number one is the result of the sum product between decision variable and the 1 and 0 value for each flight. For example, if flight H1 is operated by A350, the variable for B787 and B77 will be 0, and the formula will give a total of 1. These cells are result of some product of these two lines as well as this one. The second constraint is binary constraint, which ensure that the decision variable can only be 1 or 0. Third constraint is turnaround feasibility. If you have flight from Adelaide to Singapore at 9:10 to 14:50 and another flight from Singapore to Adelaide at 15:35 to 20:45, you might think one plane can operate both flights, but in reality, each flight requires a minimum turnaround time for cleaning and checking before the next flight. This time is called the minimum turn time or turnaround time, and it varies by aircraft type. For example, if the red line represents 60-minute turnaround time, you cannot operate both flights with one aircraft. But if another aircraft type have only 30-minute minimum turn time, which is can be seen in orange line, then it becomes feasible. These constraints reflect real-world operations. In the model, this turnaround time is incorporated into the node structure, where each node represents an event at an airport at a specific time. Different aircraft types will have different node structure because of different minimum turn time. The fourth constraint is conservation of flow or aircraft flow balance. Since this is a network model, we need to ensure that at each node, plane in equal plane out, meaning no plane disappear or appear out of nowhere. We also include ground arc to represent aircraft staying on ground between nodes, and overnight arc for aircraft staying overnight at the airport. This will be the rest of our decision variable and it need to be integer. To illustrate conservation of flow, look at one node. The arrow show relationship of plane. It doesn't mean that you will have a plane on this arrow because this will determine by the model later. So if you look at node Adelaide 9.10, you might have some aircraft that stay overnight until this time, some that are on the ground and will remain at the airport until the next node time, and also a flight that depart from this node. Let's look at relationship of flight and node in the model. Each flight is linked to node departure or arrival. The relationships are represented by +1 and -1 value. -1 means the plane departs from that node. +1 means the plane arrives at that node. So for example, flight F1 of A350 type, because the plane depart from node N11, this cell will be -1 and the flight F1 will arrive at node N31, so this cell will be +1. Then we can look at relationship of ground arc and overnight arc. It's actually the same. -1 mean depart, +1 mean arrive. Look at this line. It actually the node Adelaide 9, 10, and you can see the direction of arrow related to the +1 and -1. The decision variable will show you how many planes at each arrow. In this case, it's all 0, and the balance of this node remain balanced. This cell represent the sum product of all decision variable and +1 and -1, and it must be 0 to ensure flow balance. The formula can be written like this. The sixth constraint is allowable aircraft. In reality, the number of allowable aircraft is limited, so we need to ensure the number of aircraft used does not exceed the available air fleet for each type. For example, in this example model, we set the allowable number of each type to 2. A practical way to check this is by counting the aircraft parked overnight. Since at midnight all aircraft should be on the ground based on our assumption, so the sum product of overnight aircraft must be less than or equal to the allowable fleet. You might wonder how to determine the minimum number of aircraft required to operate all the flights. The number is that you can run this model without the fleet availability constraint and adjust the cost of ground arc, and the model can identify the minimum number of planes needed to cover the entire schedule. Constraint 7 is sustainability constraint. Total carbon emission should not exceed the target. Constraint 8 is spill cost constraint. Limited total spill cost. Too high spill cost mean too few planes or too small plane. The constraint 9 is empty seat. Control load factor efficiency. If too many empty seats, it means that the airline might use too large plane for this schedule. And the last constraint is non-negativity constraint. Ensure all variables are non-negative. The 7 to 9 constraints are added in the model to reflect better of real-world problem. The complexity of the problem. So in our work, we use 14 flight schedule with 7 airport and 3 aircraft type. The network structure is represented as follow. So this one is for B77, this one for B787, and this one for A350. After running this model, it assigns aircraft type to flight. While satisfying all constraints, the model found the minimum number of aircraft required to cover all flights efficiently. 9 aircraft in total are required. This structure reflects real-world airline schedule and ensure feasible, cost-effective operation. So, if you have any question, feel free to reach out. Thank you.